Okay, recording started. Hopefully. Yep. So yesterday we were looking at this different type of bonding, and then at some point we reached to the structure of the atoms, molecules, for especially for inorganic molecules, that how does the structure look like, or if we can to some extent we can figure out that what a structure looks like of some compound. And for that to understand or to decide what the structure of that compound will look like, we have to have some idea about the bonds, the type of the bonds, and then how much they are pulling to each other, how many electrons they have in their valence shell, how much of the electrons they can share. All those things, we have to have some knowledge of this. And we are happy that by this time we are having some basic knowledge about it, and we can use those knowledge to decide what this bond, or sorry, the molecule will look like, especially for the inorganic molecules. And we have already seen that when the electronegativity difference is less than 2, but more than 0.5, it is a polar covalent bond. If it is more than 2, or 1.9 to be precise, if it is more than 1.9, then it is ionic bonding, and less than 0.5, it is a covalent bonding. But to be honest, there is no pure covalent bond, or actually, there is no pure covalent bond, because all the electrons, when shared, somebody one at a time, some of the atoms is pulling towards it. So there is no pure covalent bonding. All right. So when we go down the periodic table, right? When we go down the periodic table, we can see that from here. Okay, we have to make it full screen. And then the presentation mode goes like this. Okay, so the ionic character will increase when we go down this periodic table, from the same group, because of that the size of the atom is increasing. When the size of the atom is increasing, their polarization is much different. The polarization is greater, and that is why they will have a more ionic character in their bonding. And also the difference between the electronegativity is also increasing, because we know that fluorine has the highest electronegativity, and as we go down the periodic table, or go left on the periodic table, the electronegativity decreases. So when there is a difference between the electronegativity between the atoms or elements on the periodic table, there will be polarization, or there will be much more tension. Polarization in this way, that there is much more tension between the two atoms, the bonding. All right. Okay. And that means much electron has been shared between them. Transferred, not shared. Shared is covalent bonding. Transferred, it has been transferred between them. All right. So as we go down, we see the electronegativity is increasing between them, difference, and the polar character of the bonds is also increasing. So Lewis structure and octet rule, what we have learned so far, we already have seen that octet, by the way, come from this Latin word that mono, di, tri, tetra, penta, hexa, hepta, and then octa, right? So from that octet came. So octet means there is an idea, or there is a state where there is 8 electrons at the outer shell of those group 2 period 2 element, so that it will become very stable. And we already have seen that it does not work very well for those element has d orbitals in it. It does not work very good for them. It's a little bit problematic, and we have to have some other consideration as well. But still, we can try to decide what will be the Lewis structure look like for it. Okay, so Lewis structure and octet rule. If we try to understand the Lewis structure and relate it to octet rule, once again, I think it deserves some explanation why we are calling it Lewis structure and octet rule, where we are matching them together is that Lewis structure is the elements are coming together to form a structure to be stable. So when they are forming stable, they are trying to form an octet as well to become more stable, to get the inert gas or noble gas configuration, and that is why Lewis structure and octet rule comes together. And by the way, I will go a bit fast. Today I have only 1 hour and I have to cover a bit. Okay, but if you have any question, you can just stop me or unmute. Please ask the question anytime. I do not mind. I like to hear some question from you. All right. So the octet rule was proposed by Lewis and Abbe at both of them together, and it works at for the two group period 2 for carbon, nitrogen, oxygen, fluorine better. And then majority of the elements from period 2 onwards, it does not octet rule strictly, and because they have d or expansion of orbit, right? They have the d orbital. Or when we go down this periodic table, when we go to the from period 2 to period 3, so there is for period 1, there is only one s. For period 2, there is 2s, right? Period 3, there is 3s and 2s and 2p coming along. For period 3, there will be 3s, 3p, and 3d. By default, these are coming along with these 3. So it is not necessarily they have to have electron and d. If they do not have electron, even d, but they have that option to be expanded towards d because they have this d by default to them because they are in 3 period, right? But 1s, if even they have a lot of electrons, they have the option to take a lot of electrons, they cannot, because they cannot expand their orbitals by taking electrons. They cannot do that. But s, 3 period, if they have enough electron, they can go beyond 3p, right? That is the option they have. All right, so that is the thing that I was talking. And then now with all this thing that we have studied or heard about this Lewis structure and octet rule, we will be going to draw some structure here like aluminium iodide. It can be aluminium chloride as well, right? Aluminium chloride can be Cl3. And for this, your information, this is aluminium, don't be confused. This is L and this is I, all right? So this is aluminium iodide. All right, so what will be the aluminium? First of all, what we have to do for drawing Lewis structure, that we have to count this valence shell electron, right? Valence shell electron means at the valence shell of each of the atom involved in this structure, how many electrons they are housing in that outer shell. All right. So for aluminium, from the periodic table, if we look at the periodic table, I cannot switch this back now. So if you have a period in front of you, you can look it back and then you see that it's 3A, right? It's period group 3A, so that it has 3 electrons. Aluminium has 3 valence electrons since it is 3A group. And for iodine, it is 7, so it has 7 electrons each. Each of them has 7. So 3 times 7 plus these 3 for aluminium should be 24 electrons together. The total valence electron should be 24 electrons. So whenever we draw this Lewis structure, we have to make sure that we keep this number of total electrons same as in our proposed structure as it appears by the calculation. If there is a difference, if it's 24 and in your structure is 25 or 26 or any other 22, it will be wrong, it will not be accepted. Okay, so how do we count it then? The easier way is easier way to draw the Lewis structure. For example, it is already been drawn for you. So I'm showing you for aluminium chloride is aluminium at the, remember the rule for drawing Lewis structure is the less electronegative will be at the center, right? Less electronegative element will be at the center, but it does not apply for hydrogen because hydrogen cannot make more than one bond. So there is another problem. There is a hydrogen exception. So less electronegative in aluminium and chloride is aluminium. By the way, if we count the total valence number of total valence electron for aluminium chloride, it will be the same thing, just like this one. So aluminium is 3 and there are 3, chlorine has 7 each. So it is 24 as well. 24 electrons as well, valence shell electron. So aluminium will be in the 3 and then there will be chlorine. We just put 3 chlorine around it. It does not matter you put it in bottom or on top, it doesn't matter. So you put around it and then in between them you join them by one line because at least they should have one bond, right? At least one bond they should have. So we can conveniently put one bond, but double bond and triple bond we have to see whether they can form with that element. Double bond or triple, we will see it later on, just now. Okay, but at least they should have one bond, and that is how they are bonded, right? So at least one bond they should have. So we can conveniently just put one dot on line dash, and one dash is representing one line, and sorry, one bond. And one bond means there are 2 electrons in one bond, right? Remember that day we are talking about that in one bond there are 2 electrons. The 2 electrons are joined by this dash line to show that there is a bonding between them. So what about the other electrons? Now we have these already 2 electrons. These 2 electrons are shared by chlorine and aluminium both. So these 2 electrons here, I cannot have any other. Oh, I can have any other. Okay. So these 2 electrons are shared by aluminium and also shared by this chlorine, same. They are sharing these 2. So you cannot say that these 2 electrons belong to chlorine or belong to aluminium. We cannot say in that way because it is shared by both. So what will happen? I mean, what is the other things? Now what we will do is to fill up the octet, we will just put the rest of the electrons to fill the octet for chlorine. Chlorine octet we will fill up. That means there are 2 electrons here already, so another 6 electron we put around chlorine, and that makes chlorine 8 electrons, and that is chlorine already is having the octet. This chlorine we will do the same thing. Okay, we will fill up, we will put another 6 electrons here, and by this way there are 2 electrons, so this chlorine also are having 6, and then these 2, 8 electrons. Same thing goes for here. We put 8 electrons all around this chlorine. I mean 6 plus these 2 bonding electron, 8. So now you see that chlorine is, all chlorine are having the octet filled up. And there are, by this way, we can achieve this 24 electron, this condition that it will have 24 electrons. So now it is, I mean, it matches our calculative number of electrons to this structural electron that we put here on this molecule, aluminium trichloride. So this is the problem that aluminium, it is an exception also that it does not fill up or fulfill this, it does not require to fulfill its octet. By this way, by having 6 sextet, it's say, by 6 it is already stable. And if I can just explain a bit, yeah, it's still time. If we can explain a bit that aluminium has 13 electron, right? So 1s2, 2s2, 2p6, that makes 10, and then 3s2 and 3p, sorry, 3p1. So now to become stable and form octet, it has to have 6 electrons. So it has to bring 6 electrons from someone else. So that is a challenge for it. But another way it can do is just release these 3 electrons, 3s2 and this 3p1 electron, and also it can achieve this neon structure, which is an noble gas, which an inert gas, right? So this is a neon structure. Bringing 5 or releasing 3, which is easier? Still, I mean, this is easier, releasing 3, and that is the idea, that it can be stable in this having. But again, it also still has some for aluminium chloride. I'm talking about for aluminium chloride, okay? It still has some attraction, or still has some desire to get 2 more electron and become stable at the outer shell. Okay, if it gets 2 more electron, then it will be stable in the outer shell. All right, so for this desire to fulfill the octet, what they will do, this aluminium trichloride, it will do is, let me draw another way, not another way here. What it will do is, okay, I take the green color. So it will, no, green is not good. Oh my God, black. Okay, so it will chlorine also here. Sorry, pen. Okay, so what it will do is, it will borrow some electrons from other chlorine. Okay, and this chlorine is coming from the same type of molecule. All right, it's coming from the same type of molecule, because these chlorine are having a lot of electrons, 6 electron each. That means 3 pairs of electron each of the chlorine are having. So what it can do is, this chlorine, these two electrons, it can donate to this aluminium, like this aluminium, because all of them are having 6, right? All of them are having 6 electrons each. So they can donate, because aluminium has a long affinity for electron, a lot. So, and the chlorine are having excess of it, not excess, just enough, and this is lone pair electrons. They are not doing any loitering there, so they are able to donate this electron to aluminium, because aluminium is attracting very strongly. So this type of bond is called a dative bond. It is called dative bond. We will see in boron trifluoride, ammonia, will be a dative bond as well. So this is called dative bonding. DIVE. Okay, dative bonding. So this type of bonding is dative, and for your information, aluminium dichloride, all right, so if we heat it 180 degrees centigrade, it will sublime. It will sublime means it will go from solid to straight to vapor. It will go from solid to straight to vapor state. So that means it's sublime. And when we try to find out the molecular formula of this, or the atomic mass, molecular mass of aluminium aluminium trichloride, we find that the aluminium trichloride we always find it is like this, Al2Cl6. It is not Al and Cl3, not this way we find. Only when it goes to the paper, we will find it AlCl3. But normally the calculation it gives us, the molecular formula is this. So this is the explanation that why we always, if we try to find out by calculation the molecular formula of aluminium trichloride, why it will be a Al2Cl6, because it is a dimer. It stays as a dimer. Okay, now phosphorus pentachloride, another exception for this octet bonding, because phosphorus is not from this 2-period element. So it can expand its octet because it has d orbital in it. So phosphorus pentachloride, there is 5 fluoride atoms are here, ions in fact. So fluorine, each of them are having 7 electrons, right? Each of them are having 7 electrons, fluorine, and there are 5 fluorine atoms. And phosphorus has also had 5 electrons, so altogether is 40. And for when it becomes 40, this is you draw phosphorus first and then put the fluorine around it, 5 fluorine, because there are 5 atoms of fluorine around it, and just make the bonding between them, because at least they will form one bonding, and fluorine cannot make more than one bonding. So fluorine is only one bond. So that is, and fill up the octet for fluorine. By this way, we see that this is 8 bonds, right? 1, 2, 3, 4, 5, 6, 7, 8. So 8 times 5 is 40. So it satisfies on both sides that we have 40 by calculation and 40 from the structure we can see. Nitrogen dioxide then. But there is one problem is when there is nitrogen, all right? When there is a nitrogen, so we be a bit careful about the nitrogen structure, because there is always, this is problematic. When there is nitrogen, there is always problematic, so you have to be a bit careful. Okay, so the Lewis structure of nitrogen dioxide, the total electron number is 17, and we can draw in this way. There are many other possible structure we can draw. I'll show you in a bit, but we have to find which one is more stable, or which one can be more what do you call it? Which one can be a bit more plausible or possible that they can stay stably? Yeah, they can be stable. For the word, what I am to say. Okay, but here in this way we see that there can be a negative. I mean, one single atoms on the electron on the atoms as well, unpaired electrons. That is possible as well. So exception of octet rule, all right? Exception of octet rule is, okay. So exception of octet rule for boron and for beryllium, okay? And for phosphorus, those who has less incomplete octet, because they are 2s, 2 period 2 group, period 2 element, and for phosphorus and sulfur, and we know that they have expansion, they have d orbital, so they can expand their octet, and they can have more than 8 electrons in it. And sometimes there will be odd electrons as well for you know, for some elements or some molecules, there will be some odd number of electrons, and they can form a free radicals, and because of those free radicals they are very, very reactive. Sometimes we can see. All right, so these are some of the exercise. I am assuming that you have tried at least some of it, and you have seen that it is some of them are quite easy, and I can ask you to show. Of course you will not do that, I know, but I can show some of the easy or simple molecules, how to find see the Lewis structure. So it will be CH3Cl, ammonia, water. Okay, I will not show all of these, and then chlorate, phosphate as well can show 3. Okay, multiple bonds we can do. All right, so before we go to that sulfur tetroxide, I want to draw this simple structure first for your understanding, that CH3Cl, right? The previous slide we have seen CH3Cl. So how do we draw it? Carbon, the total valence electron, TVE, you can say the TVE, total valence electron for carbon is what? 4, right? Is the 4A group. Group, yeah, 4A group, and so it has 4 electrons at the end. Hydrogen has 1 electron on each of the atoms, so there will be 3 times 1, 3, and chlorine are having 7 electrons at the outer shell, so altogether is 14 electrons. And now if we draw Lewis structure, so which of them should I put in at the middle? Which of the atoms should be put at the middle? Anybody? Okay, carbon, because carbon is less electronegative. And then there are 3 hydrogen. I have to put 3 hydrogen and 1 chlorine around it. Oh, sorry, not this way. I do it this way, so. Okay, so what you have to do is, let's put hydrogen here all around it. You want to put hydrogen here or chlorine here, let's say, no problem. You can put chlorine here, or you want to put chlorine here, also no problem. But for time constraint, I just do it faster, so I put hydrogen all around it. So what I do is, now because hydrogen and oxygen, there should be at least 1 bonding, I just make 1 bond each. All right, and then we make the fill up the octet for chlorine, right? For hydrogen, do I need to fill up the octet? Do I need to fill up the octet for hydrogen? Hydrogen cannot, because hydrogen does not have the capability of take more than 2 electrons, right? It cannot, I mean, it is its size, it cannot expand, it will break, right? If it is expand, I mean, just metaphorically I'm saying that it will break. So that only chlorine will have 8 electrons, hydrogen only will have 2 electrons, because 2 the maximum electron it can take. It has only 1 s orbital, but for carbon it can have 8 electrons, and it is already having 8 electrons. Each of the bond is representing 2 electrons, so it is having 8. Oh, it is not double bond, yeah, it is single bond. Sorry, it is single bond. It's not double bond. So each of the bond is representing 2 electrons. Carbon are having 8 electrons in it. So now this is 1, 2, 3, 4, 5, 6 to 8 to 10 to 12 and then 14. So altogether I have 14 electrons here by calculation and by the structure, from the structure. So that is what satisfies the structure of Lewis structure for this methyl chloride, okay, or CH3Cl. Okay, and then now we move to another one. We try to do another one. This is what I'll do is water, H2O, H2O, H. Oh, I shouldn't do actually. I already have done hydrogen. Okay, so hydrogen has two. Each of them has two total valence electron. I mean, each of them has one. So 1 plus 1, 2 hydrogen, because 2 is here, plus 6 from oxygen. Oxygen has 6 electron at the outer shell because it's from 6A. So altogether has 8 electrons. All right. And now, because hydrogen cannot be at the center, we have to put oxygen in the center and hydrogen by choice. You have to, I mean, we put it on the outside. Why we do not put it here to hydrogen? Because they are also atoms, and we are also made of atoms. So like human, they also want to be free and at easy. So if there are two hydrogen far apart, they can have much space to enjoy, and that is why they will stay far away from one another. And now we have to join them or show them by two bonding, because they will form the bonding, and the rest for oxygen, hydrogen, there is no more needed because already two filled up. For oxygen, there are 4 electron left to fill up the octet. So we just put these 4 electrons around it, and that will make it the octet filled up. So 2 to 4 to 6 plus 2, 8. So altogether it has 8 electrons. Okay, so this is what the simple structure looks like. But now let's move to this ionic molecule, or ions actually, ionic molecule. That what we have seen is that ClO3, right? Just now we have seen from the previous slide, ClO3, and it has one negative charge. It has one negative charge. Very clearly it is shown that there is a one negative charge. So what is the total valence electron for chlorate ion? This is a chlorate ion, so ClO3 negative. So what is the total valence electron for this chlorate? Chlorine as well has 7 electrons at the outer shell, valence shell. Oxygen, 3 oxygen, each of them will be sharing 6 electron each. So altogether is 18, 3 times 6, 18, plus, since it is having one charge, right? It is having one negative charge. So it will be, a negative charge means it has one extra electron, right? It has one extra electron, that makes it a negative. So one electron should be added up. If it were a positive charge, let's say some kind of ion that is a positive charge, so we would subtract 1 electron from the total number. So in this case, we see there are 18 plus 1, 19 plus 6, 26 electrons. It should, this ion should have 26 electron altogether, and oxygen is more electronegative than chlorine, so I just put 3 oxygen and the 3 around 3 and make 1, 1, 1. Right, and what else? We have to fill up the octet for oxygen and all the oxygens like this. All the oxygens, we fill up the octet. Okay, we fill up the octet for so by this, how many electrons are there actually? 2, 4, 6, 8, 24, and then we can make these 2 electrons on the chlorine, and that makes 26 electron altogether. So here is 26, 8, here is 8, here is 8. So 3 times 8 is 24, plus this 2, 26. So it satisfies the calculative value and the total number from the structure, the value from the structure. But there is a problem that it will not, that is not the structure, I mean, most stable structure. This is one possible structure, but not the most stable structure for this chlorate ion, because they have something called formal charge. They will have some formal charge build up, and because the higher the formal charge, the more unstable the atom or molecule or the ion is. If we have less formal charge, or let's say the best formal charge is 0 for all the atoms involved in this molecule. But if we have higher the formal charge, the less stable it is. So now this is not the most stable chlorate structure. It's not. So what is the most stable chlorate structure? How do we know? We have to find the formal charge on them. To know the formal charge, we will go now to see. We will come back to this chlorate later because we haven't finished it yet. So we will move to this sulfate ion to see how or how many possible way the sulfate ion can be formed. All right. So let's see that here the sulfate, the same way we put the oxygen atoms all around it and found the total valence electron is 32. So found it here and fill up the octet. But there is another way that we can put it, we can draw in this way, that we add these 2 electrons, we bring it here, we bring these 2 electrons here to form, because one bond needs 2 electrons, right? So if we bring these 2 electrons here, there will be 1 bond here. If we bring this 2 electrons here, it will be 1 bond here. And then of course we have to remove the electron from here. We have to remove the electron from here because this electron shifted here to form a 1 bonding. And then by this formation of bonding, it is also, I mean, by this way we see that there are 32 electrons as well here. Here is 32, there is 32. So in both cases, there are 32 electrons. But which one is most stable? Which one should be more? And sulfur, of course, because it has an expansion of octet, it can have, so it can have more than 8 electrons in it. And that is why you see here 2, 4, 6, 8, 10, 12 electrons sulfur is having. So which one should we choose, or which one do I choose to say that this one is the most stable sulfur atom, ion, sulfate ion? Now, formal charge comes into this place. So formal charge is actually how much the charge that atom is experiencing because of the electron differences around it. Okay, around it. And it can be calculated. It can be calculated from this formula, that formal charge on any atom or an atom involved in this Lewis structure is the total number of valence electron of that atom. Okay, total number of the valence electron of that atom minus the total number of non-bonding electrons at that structure, that is after the structure has been formed, how many non-bonding electrons or unreacted or available electrons it has, minus half of the total bonding electrons, that is forming how many bonds. Each bond is having 2 electrons, so how many bonds it is having, half of it we have to subtract from this total number of valence electrons. So then we will find the formal charges. For sulfur tetroxide, when there is no double bonds, between sulfur and oxygen. The formal charge we can calculate because sulfur, it is from the 6A, and we know that it has 6 valence electron. And, I mean, normally it has 6 valence electron, right? So that 6, for these cases, sulfur will have a 6, that is the total valence electron from the electronic configuration, or from the periodic table we can see that it has 6 valence electron. And now there is no non-bonding electron, there is no unpaired electron. All electron on sulfur has been used up. There is, like this, on oxygen there is non-bonding, or sorry, one unpaired. Here is one unpaired electron, another unpaired electron, one pair of unpaired electrons. So on every oxygen there are 6, right? 1, 2, 3, 4, 5, 6. Every oxygen atom are having 6 non-bonding electron, but sulfur is not having any, as at least we are not showing here any, right? And by not showing, we can satisfy 24 electron on it. So there is no non-bonding electron on sulfur, so there is 0 in here. And how many bonds sulfur is making? 1, 2, 3, 4. 4 bonds it is making. Each bond consists of 2 electrons. So 4 bonds is 8 electron and divided by 2. So by this way we see that sulfur has positive 2 charge. Right? Sulfur has positive 2 charge. Okay, there is a problem here. Let me, I have to draw it again. Oh, it is supposed to be this. Okay. No, hold on. Copy and then paste here. I don't know how it changes. It is supposed to be this one. This molecule. Can you hold on, please? I need to take a call. Hello? Hello? Okay, sorry for the interruption. All right, so for the formal charge for these 2 atoms, 2 things, all right, everything set up. The time is running out. Okay, so for these 2 possible structure, formal charge we see here. Formal charge for this sulfur we see here is positive 2. On this sulfur it is having positive 2 charge, right? And on oxygen, each of them have negative 1 charge, negative 1 charge, negative 1 charge, and also on this oxygen is negative 1 charge. For this structure, that possible structure that we have made, on this sulfur, there is no net formal charge. It is zero formal charge. And these two, oxygen that is single bonded to the sulfur is each of them are having one negative charge. And for these two oxygen, which is double bonded to sulfur, each of them are having zero charge. So now altogether, and by this way, we see that this 2 has been cancelled by this 2 and this negative 2 stays. And that is why we say SO4 2 negative, right? This 2 negative charge is coming from this 2 negative ion, and this positive 2 charge has been cancelled out by this negative 2. Okay. But for this, we see that there is only no positive charge, only 2 negative. So which one should be the best choice for us to, for this structure? As we say that formal charge, which one will be less formal charge will be the most stable. And for this case, we see that here, although it is cancelled out and stay as 2 negative, but on this case, we have less charge, we have less dispersed in the charging, so that means it is more stable. So when we choose the plausible or possible Lewis structure, which will be the Lewis structure is for neutral molecule having no formal charge, it is 0 is preferable. Neutral molecules, when we call it neutral molecule, that means they are not very electronegative. Okay, they are not very electronegative, and neutral molecule means they are not carrying any charge. Okay, so those who are not carrying any charge, that is H2O, right? It is not carrying any charge. NH3, it is not carrying any charge, but ClO3, just now we saw ClO3, it is carrying any charge, so it is not a neutral. These two are neutral. So it will be plausible, or it is most acceptable when there is 0 charge. It is not must, but it is preferable. The smaller charge, all right, the smaller formal charge are more better than bigger formal charge that just now we have seen, and negative formal charge should be resided on the more electronegative atom. So for just now we have seen the electronegative atom oxygen and sulfur was there. In case oxygen was positive charge and sulfur was negative charge, that would be a very, very, what is called that, unlikely. That would be much unlikely. That is almost, it is not stable. The negative charge should be on the electronegative atom because they are more electronegative. They are more electron. They attract more electrons. So the negative charge should be, if there is a there should have to be a negative charge, it should be on the electronegative atom. And similar formal charges on adjacent atom are not desirable. What it means is similar charges on adjacent atom are not desirable. That means if I could have drawn this structure, right? This is not possible. We already have seen because it is bigger charge difference. It is much possible. It is acceptable. But again, even if I would draw this structure, where should I draw it? If I would draw this structure in this way, S, and then this 2 is 0, O, this O, and there are 2 oxygen atom, each other, 1, and then each of them are carrying 1 charge, right? Formal charge, of course. It would not be desirable because since they will be carrying negative charge, and this negative charge will repel each other, so there will be more tension between them. But if they are far apart as much as possible, there will be less tension between them. So that is why they are stable in this way rather than staying side by side. Okay, so in this way it is more stable. But the another empirical data is when we are saying that here these two oxygen is having the double bonds, right, with sulfur. In actual case, it is not the thing, that it is not the case that this double bond, it does not stay here and then this negative charge does not all the way or all the time stay in on this atom only of oxygen. What will happen is they will rotate. They will rotate, one by one. So for example, at this position, we see that sulfur is having two charge and each of them are having one negative charges, right? So this is most plausible or most possible. And single bond is bigger than double bond. Can anybody tell me? I have some Menti question, but I think I cannot continue today. Single bond is shorter. Single bond is single bond is longer than double bond. Anybody has idea why? Double bond, because there are two electrons, right? 2 to 4 electrons are involved in the double bonds. So that means more attraction between them. They are and more stronger. That means more attracted to each other, more stronger they are, and that is why the bond length is shorter than the single bond. So what happens when about the charges? Actually, they don't. We as we denoted or we said that it will be far apart. It will stay far apart, but it is not always the case. They will move around. It will go here and then it will go here. This will go here and then this charge will go here. Sorry. And this one will form another charge. Okay, so this one will form another bond and then this bond will go. So it is rotating by breaking and forming the double bond with all the oxygen atoms. So here we say this was the structure that we say is most plausible and possible, right? But the other forms of the structure is happening in this way. So this charge, it is not situated or stationary in one position. It is moving all the oxygen, because the oxygen atoms are all the same oxygen atom. There is no difference in oxygen atoms. They are all the same thing. They have the same property. So why only this oxygen will carry the negative charge and this one will not carry the negative? That doesn't make sense, right? So this negative charge will go all around these oxygen atoms, of course, by turn, and it happens in a very, very fast, in a almost the same time. Here is negative charge, and then the next moment, not time, moment, or very smaller time, I don't know how small you can think about the time, it will be, the negative charge will be there, all right? So it is rotating all around, and that is why it is called the resonance structure, okay? A resonance structure is one or two of the more Lewis structure for a single molecule that cannot be represented accurately by only one structure. We cannot say that this molecule has only one structure. Resonance structure is actually just now we showed that it has a different types of different form of the structure. So that is the resonance structure. For example, this is an ozone, right? Ozone, I'm sure that you have heard about ozone and ozone layer. So this ozone, the 3 oxygen atom is attached in this ozone layer, and some of them are positive, some of them negative. But this oxygen atom and this oxygen atom, they do not have any difference. They are the same oxygen from the same periodic table, same property. So this charge will move around, or charge will move along this, and this charge will be formed from positive to negative, and then this is how sometimes this atom will carry negative charge, sometimes this atom will carry negative charge, and that is how they will be stable in this way. If we do not allow, I mean, if you think that I would not allow it to be in this form, only this form, then the tension between them is very high and they will not be stable. But because of their resonance, this ozone is stable. It was not supposed to be stable that way. Okay, the formaldehyde is one as traditionally, and they have resonance structure. Which one is more possible? From the formal charge that we count, we can find the formal charge. And during the tutorial class, I will show some more example of this. We'll draw more structure of the list, structure and formal charges. We'll calculate and see it. So this is it. Do you have any question, anyone? Does anybody has any question? Calling once. Calling twice. Okay, so you don't have question. That's good. Okay, so I'll see you on next Monday. Those who are coming for the lab, and those who are not coming will be connected through the MS Teams, the same link. And otherwise, I will see you on Tuesday. Not otherwise, and then I will see you on Tuesday for the tutorial class. All right, take care. All the best. Take care.